Well, hi, good morning. Thank you for joining me in my shop. Today is October 13th. And what's happening with this radio? Wow, that's a good question. So I worked out a basic theory of what had probably happened, and I identified a particular resistor as probably the one that burned up. And sure enough, when I look in the radio, when I look in this part of the radio, I can see the resistor, and it's definitely burned up. But there's another resistor burned up. An unexpected burned up resistor. And for the life of me, I cannot explain how that happened. So I'm just going to show you here on this diagram what I'm talking about. So the resistor I figured must have burned is this one here. It's this one here. So those two tubes are pretty identical circuits in them. So looking at the wrong tube there to start. R6 here, and sure enough, R6 appears to be burned up inside here. But I also discovered what looks like this one, R5, has also been damaged. R5 on the sheet here, if you can read it, and I guess you can't. It says 510 ohms, but I measured it at 90 ohms. So there's a number of versions of this radio. I suspect this particular part is hardly changed, if changed at all. So I start wondering if the observations I'm making don't add up with the schematic. Maybe I've got the wrong schematic in front of me, but I don't think so. I think the radio is quite consistent in this area. So I studied here for a while yesterday and tried to come up with a story and explain how you burn these two resistors out. One of the stories, a really bad story, would be a short taking place inside this vacuum tube. So what I did was I took this tube, I also took this one, they're both 6BA6s. I put them in my tube tester, sorry, each one for about a half an hour. No, there's no shorts in these tubes. So that story's out the window. So I've been tracking it back through here, but there's a problem in going through here. You have to have this one shorted. And from my study of this, there is no B plus in this area. There is no way for current to come out of here, even if this was shorted, and come down and do something. There's no path. There's no source. So I have no explanation for how it is this resistor and this resistor burned. I mean, this one's easy. This capacitor shorted, this resistor burned. When I tested this capacitor, it's not shorted. Now, this raises another question. I'm not sure what to say. The capacitors in this radio are not of the usual type. Here's one of them right here. Inside this is a ceramic tube, or a tube with ceramics on it. I think that's a better way to put it. And the exact construction in here I'm not quite sure of. Nevertheless, it may be possible for this type of capacitor to heal after shorting. It wouldn't exactly heal, but what would happen is the short circuit would be burned clear. And I worked in the power company. This would happen with power cables. You can have a fault, and you have a huge arc on a piece of cable, maybe with a conductor, the copper conductor could be this dimension here. This could be the copper part of the cable. And so when it shorts, the huge current flows from here through the insulation, which is often wrapped paper, believe it or not, gets to the outside of the cable, which is a lead sheath, a particular kind of cable I'm talking about. In just a few cycles of power, a few fractions of a second, it'll blow away a whole bunch of copper in here, burn away, vaporize the paper around it, and blow away the lead on the outside. So you got a hole in the cable this big. But the lead outside, which is grounded or part of the neutral system, is not touching the conductor. They never touch. If you were to, and what will happen is during the fault, just like in your house, a circuit breaker will open, and a big circuit breaker in a power station will pop open. An alarm will go off at the control center that one of the big cables is out of service now for some reason. They may attempt to re-energize it. It's possible they may do that. They close the breaker in the station, and this fault doesn't reactivate. It just sits there. You have a big chunk of copper like this, and then some paper exposed, and then the lead around it like this. Now the dimensions aren't right. I'm making them overly big and stuff a little bit smaller. You want to talk danger? That is dangerous, because now the cable's energized. Everybody thinks, oh, it must have been a tree limb, until somebody goes in a manhole and finds one of these. And I'm that guy. I am that guy who went in a manhole after a cable failure. As my usual part of my job was to determine what caused the cables to fail. I go in this manhole, and you know the cable, all told, is as big as my arm here, and I'm looking up the cable like this. It's dark and dingy in a manhole. You're underneath the street, right, with a little flashlight trying to see it. And I'm up close, and I go, what's that? That looks like copper up there. And I put the flashlight on. Oh my God, it's exactly what I described to you. Copper conductor sitting there, insulation here, 2,000 volts on it, and 1,000,000 amps ready to go. Boy, did I beat it out of there. So, now, getting back to this. Could that happen in one of these capacitors? Develops a short circuit, and the short circuit burns away material for a short while. Yeah, short circuit, short while. Until the material is burned away so far, the arc stops. Now, I'm doing it like this, but we could be talking about very, very small dimensions inside this capacitor. Then I come along later with my ohm meter, and I put the ohm meter on it, and it seems fine. You know what? If it short, just thinking about this a little more, if it shorted inside like that and did manage to clear itself, I think it would still show a high resistance. It wouldn't show an infinite resistance like these capacitors, when they're good, do. So, but I have to accept that that's a possibility. The reason I'm doing these tests and not finding a shorted capacitor is the capacitor has healed itself. Is that likely? I don't know. I don't know about these capacitors. It's not likely in a power cable, I'll tell you that much. It does happen, but it's not likely. Well, I think the best thing I can do is repeat the investigative tests I did on here, looking for and examine that resistor, the two resistors more closely, and repeat the attempt to find a shorted capacitor, and really work at this, because surely to goodness there's a shorted capacitor in there, isn't there? Okay, that was a long talk. How long did I talk for just now? 7-8 minutes. Oh, I apologize. Okay, so I'm going to get some coffee, and then we're going to start poking around here. Okay, let's start with a visual examination once again. The resistors in question are this one here, which looks burned. And this is the one that measured 90 ohms instead of 510. And then the other one is just back in here. I'll use a different camera here. We'll take a close look at these two resistors. Maybe there's more in there. You know, this is just what I found. Okay. So the one there you can see with the 3 orange bands is not one of the suspected resistors. The one to the left of it is. So you can see the color bands they look like they've been roasted. And in the back there, also a little to the left, I think yesterday I was able to sort of tell that the resistor was cracked right in two. Let me try pushing on it. If I can get in there. Oh. I just touched it, and I think pieces of it disappeared. I think that's what happened there. Let's take a look from the other side. Now, is there anything else in here that looks roasted up? Not that I can see. Okay, I'm going to turn this right over. I'll look at it from here. pieces of debris. What is that? Oh yeah. I think that's a burned right through resistor there. I don't think there's any question of that. And that's R6. There is no question about that. Okay. And nothing else appears to be fried up in here. And there's going to be no evidence in the capacitors of which one might have shorted, but we know which one it is that might have shorted. It's the one that's hooked up to R6. It's this one right here. Okay, so why don't I just put the ohmmeter right away on that one. So I may have yesterday just somehow missed testing the critical capacitor here. I'm sure I did, though. I'm really sure I did. Okay. Maybe I'll put this down here. So there's a wire with black covering on it coming right to this terminal here. And the other end of that resistor is most certainly tied to the chassis here. So show me a short. Okay, on the basis that maybe it's I can detect a high resistance leak in it now. I would guess what we saw there was a charging up of the capacitor. Yeah, the pieces of resistor are just raining down inside there. No explanation of what happened here. I suppose I could remove this capacitor and do a high voltage test on it and see if it breaks down under high voltage. Pretty, like I'm probably on my way to changing all these capacitors in here, which is a fairly involved task. But I'd really like to be more sure of when it's happened. So let's repeat those tests. Yeah, we don't have to repeat it on R6. That's the other one. It's R whatever it was. I got 90 ohms last time. I think I looked on the schematic and there's no explanation other than it's a 90 ohm resistor. Okay, so we're trying to touch the lead here. Oh, I'm way up on the wrong scale. There we go. 94 ohms. And I think I mentioned I've always kind of believed that resistors go high, they don't go low. But this one appears to have done that. Or is this a different value? And when I looked at the color bars, they were ruined on it. Is it a different value in the like, there's a number of different models here. So I'm going to look through some information I have and just see if I can find a different value for that capacitor or a resistor, which I highly doubt. Well, here's something interesting I've noticed here while I've been looking at this. So you see every capacitor in here looks like these very same style of ceramic capacitor. Look at this one here in particular. There's no question that's a ceramic capacitor, just like all the rest. But take a look at what's in this actual radio. The same capacitor as this one. And this very much looks like a electrolytic capacitor, but at the same time I can see that its size is 0.01. 600 volt, 0.01. Why is that there and not another one of these? How did that happen? I hear you, Bert. My cat is meowing at me down there. Here's the other side of it. So this looks redone. This definitely looks redone. So somebody's replaced it with this capacitor here. What's written on it? Yeah, I hear you, cat. I'm expressing frustration at the cat, but it's really the radio I'm frustrated with. Well, you know, the only reasonable conclusion is this got replaced. That's a little weird. That's a little weird. Hang on there, Bert. Okay, I'm coming. I have to go play with my cat. Okay, let's take a look at this on the schematic here. So this capacitor here, which has been changed out, is a C23. A C23 is this one. A C22 is the one that I figured had shorted. C23 is the one that's been replaced previously. C23. So what if this one shorts? So this is the incoming B+. Like I said, it's just a capacitor. It goes to ground on the B+ line, which then continues on it this way. If this shorted, it would draw a heavy current through this line here. And if it went through any resistor, it would burn it. Well, it might burn it. Okay, so we're still looking at this line. It's coming all the way over here. I think I lost track of the line because I've ended up here. I'm not supposed to end up there. Let's try it again. So we're on this line. The second one up. Second one up. Yeah, second one up. Turns here. Comes down. Attaches here. Well, from here, it's a straight shot through these two inductors and on to the fuse here. How do you do that way? Coming the other way. Coming in the other way. Coming in. Hello. Where? Oh, here, I couldn't see it because of the crease in the line. Here. So here are, so you're going to come in through here, or draw current out of here, and it's going to be drawn through this fuse. So the only thing standing in the way to current flow from that capacitor shorting is this fuse. So I think what probably happened was radio stopped working, fuse was blown. Fault was tracked down to this capacitor shorting. They replaced this capacitor, did nothing else. Put the radio back together. Put a new fuse in it. That's what I think happened there. Okay. Because I would expect any one of these capacitors fails, there's a resistor that goes with it. That's not necessarily true, but that's what I was thinking. Probably true in most cases. They've never really studied this wire down here. This is the wire that goes to the crystal oscillator, and it's just a bare wire just coming through this insulator. It could pretty easily make contact. There's great insulation here, but nothing on the other side really. You can make a short there pretty easily. And then coming straight to one of these clamps. Well, I'm milling around here because what I'm looking at in front of me here is a headache, because I don't want to go ahead and start doing things until I understand how things got to be the way they are. How did R5 burn up? How did R5 burn up? So that's the real question here. I'm not going to find it there. I'm going to find it way back here. Here we are. there's R5 there. The only way it can burn is heavy current. Heavy current could maybe come through the tube. How else could you get a heavy current there? If it's not through the tube, how could you get a heavy current there? You got a capacitor here blocking any current. Assuming the capacitor is good, there's just no path. There's just no path to burn this. Unless something really dumb happened. What really dumb thing, like stick the wrong tube in the socket? I didn't do that, I promise you. I didn't do that. The radio was operating, and then this happened. Could it be that this thing's been 90 for a long time? And while I'm looking at this one, I noticed this one. And this has been this way for a long time because of something previous. Could somehow this one cause this one to burn? How could that possibly happen? So if this is shorting, you just have a heavy current going this way. You would drop the voltage supply. You'd drop the voltage supply everywhere probably. Just curious how they've drawn this. Well, what if this failed? So let's suppose this one failed. So there's a short here now. Well, you'd have B plus supplying the short back this way, and you'd start having, you could start doing stuff in here. You'd get what's a 51 ohm resistor there. It would take the whole thing. There's another 510 down here with a capacitor making sure the current comes this way. And you're down to here. This is where it gets a little confusing. You're coming along. I don't think there's anything here. You just come along, going up in here. Up in here, up in here. Going through capacitors. So here's a ground over here, but you can't get to it because of the capacitors. So I don't think there's a ground in here that current B plus could find this way. How do you burn this out? Or that's just natural degradation. I've never seen it before. I have a lot of these 510, 510, 510. Another fusing, doing like a fuse thing. There's a 510 here. Oh, that's 510K, not 510. They just had a whole bunch of, they just like buying 510. That's a K. There's no K here. There's no K here. Now these two circuits are very, very similar. Well, I can't find any explanation for what happened to this resistor. Something really weird happened. Like some short, I can't believe it. The radio was operating, and then it wasn't. It's a red herring. This is a red herring. Perhaps this is a red herring. It is carrying plate current, so it's working a bit. But it's only 500 ohms. You know how much plate current can come down through here? 5 milliamps. 5 milliamps and 500 ohms. That's what, 10,000 kilowatts. Boy, oh boy, boy. Maybe that's what happened. Maybe you know, my understanding of resistors is false. They can go low. Maybe this thing warmed up because of current flow. If it went low, what would happen? I got 1,000 here and 500 there. And together, they really don't amount to much in these circuits because typically, well, you know, we've got an inductor here, so I don't know what to say, but typically, plate circuits have thousands of ohms in them. I guess that would be happening. Maybe, no, that's the signal going out this way. thousands of ohms for the signal. Oh, here comes Bert. I've probably done enough thinking for just now. I've depleted the sugar in my head. I don't put sugar in my coffee. Maybe I should start putting more sugar in my coffee. What, what do you think, Bert? Do you have any ideas here? Are you able to help me out at all? No, you're inspecting the lighting system. Okay. We didn't get anywhere here, but this is how it goes. So I'm going to get off the keyboard, cat, please. I'm going to take a little break here. 9 minutes. I thought I'd look at a different schematic layout, and maybe I would see an explanation for how this guy gets burned out. So if we so this is the B plus coming in here up through R4, which burned 5, and this 510, which appears to have been damaged through this coil. If we come down this way, there's a capacitor here. So you wouldn't expect any DC to flow. This will be like high voltage, DC voltage here, a high DC voltage here. But there's a capacitor stopping current. But what if this one shorts? Okay, so C24 shorted. Now, what can happen? The B plus can find its way down here. We're into the little segment circuits that get rotated when you change bands. So it show you one segment here. There's another one here, another one here. See these numbers, 4, 5, 6, and 1, 2, 3. These are the that's a crazy way to number them, isn't it? These are the contact fingers. So I think what they're showing here is the this one here, I think. This is, wait a minute now. I didn't have it there. I had it. Where's the where there's another one. Where's where's the one? 135 to where's, oh, it's up here. Oh, okay, so they've shown one of them actually right in the circuit here. Good. This is the one I had to read a switch to. So this is the circuit it was facing. So okay, this guy, yeah, this guy shorts. B plus coming down. 51 ohm resistor is not going to stop anything. Coil here, who knows? You're facing this resistor, 27K. That's pretty high resistance, 27K, but look, on the other side, right to ground. So there is another ground path on the failure of this one. We got to find this capacitor and test it. C24. We must find C24. C24, 25. C24 is this one. I'm looking back at the coming up to the, oh, I got this turned. I'm looking at it totally wrong here. Still looking at it totally wrong. Okay, I see it now. I see it. Okay, let's look at the radio here. Okay, so we're talking about this capacitor now. Let's check it. The problem with this one failing, and my eyes are open now about something, it would strike me if some of these capacitors fail and the radio stops working and you grab the band switch and start rotating the band switch, you might accidentally be putting more and more components at risk inside these little segments you see down there. So you could sort of successively do more and more damage while you're innocently flipping bands. Now I've heard of that happening. This guy, is he shorted? comes up to this one, doesn't it? Well, let's check the other one too. No, it's this one. So, not short. Did I get this in here? Let's check. Should short. Okay, and here. No. So no short on that. Or again, did something like this short under voltage and then sort of self-heal in a way, and so now I can't spot it. I thought I had the explanation. Wait a minute, the capacitor I'm checking, isn't it in the no. For the problem to happen, this would have to fail first, and then you'd have B plus traveling down into the segment inside the radio and doing more damage down there. Gee, could we see that? Because if this thing is healed and I'm testing it and getting, it looks fine when it really isn't, the damage could be down in the radio here. Why don't you look into that? We'll look in the radio and just see what we can see anyway. Part of the challenge now is to see the segment that in fact might have a fault in it. So I have another camera looking in the back of the radio at the segments. Okay, and what I want to do is figure out which segment is which. So right now we're dialed up for the 3 to 7 megahertz band, and so what that means is the contacts that are facing upwards, these guys here, these are the 3 to 7 band. I'm going to change the band here to the same one I had on this way. Because I was listening down here. So we're on the broadcast band now. So that means the broadcast band is these ones that are up, but you can't see the components, they're on the other side. So the trick now is to rotate that downwards and look down and see some of the parts, and goodness knows if we can see anything this way, but I'm going to give it a try. Let's just stand back a little bit. Okay, here, I should go up, have a look down too. So, So this is the one I want to look at. Now I could pop it out. I've never taken one of these out. And there was a special tool that they show that pushes these tabs apart or something, and then out comes the part. And I'm not going to attempt it right now. We just want to look. So what are the parts behind this one? So let me do the band thing here. Okay. This way. Maybe about like that. Okay, now we're going to look with this camera here. Oh, Bert, not right now. You just come in right at the wrong time. So now we're looking down in there. Well, see anything? Yeah, well, look at the coil. Look at what you can see. What can you see? So there's a good chance I'll be taking some of these out because I have these capacitors in it, and if I am on my way to changing all of them, and I'm pretty sure that's where this is headed, I'll be taking a number of these out. There's one up in there too. Just I think in this low frequency band. There's another one over here. They're everywhere. Yeah, and that means in my other radio, I have never gone in and changed these capacitors in my other radio. And I believe they are paper wax, unreliable capacitors. Maybe that radio will come back in here someday, and I'll do these. There's not a lot more I can do here. Really, just like this. Okay, buddy. Man, you are a very persistent cat. He's ready to go. See, he's pointed in the direction he wants to go. Bert, you want me to go out there? Yes, that's his answer. I have to go play with the cat again. So I want to continue to avoid taking out any of these. I'm not ready to do that yet. But I do need to see the resistors. We didn't see them. The resistors that are behind here. So I think we're going to get a chance if I look down through here to see them. If I just turn this about like this. Yeah, I can see one down there. Okay, so I'm going to change to this other camera, and we'll figure it out. We will figure it out. You can see a little bit of the resistor down there. Does that look roasted? Not particularly. Now there's two resistors in here. So that's one of them. Let me look at it the other way around here, changing hands. Let's see if we can see the other resistor here. Oh, little hole. Spy hole. I don't see it. I don't see any of it here. That resistor we do see doesn't look terribly healthy. What would you say that is? Green, brown, orange. 51K, but I 51. Wasn't it? What was it in here? Hang on a second here while I'm just going to drop the camera for a moment and take a quick look myself at this was so there's a 51 ohm resistor in there and a 27K resistor. So it's definitely 51 ohms. It doesn't and that's definitely green, brown, 51. But then it's orange, 51K. What is happening now? Can I get another look from the other way on this? Let's see if we can do that. So here it is. This is the one here. Yeah. Oh yeah. There's the other resistor there. And a bird is showing up. Well, that again. Oh, look at that. Is that the same one? It's 51. That's black. So that's 5100. What would you say? He's climbing up my back of my pants here. Bert, just hang on a second, because I'm in an exciting moment here. We can test these. I can get probes in there and test that stuff. Okay, here I go again. I'm coming. Oh my gosh, this cat is running my life. You're running my life here. Yeah, there he is. He's the guy. You're the guy. Show him what you do. Show him what you do. Flop right on the ground here. No, this is not ground flopping area. Notice I've taken the rug from down the hall and took it into the rec room so he could play more on the rug, because he loves playing on the rug. Okay, enough. I'm coming. Okay, let's take a look at the resistor that's exposed here now. Oh, we were already looking at this, weren't we? I guess I forgot when I went for my coffee. I was going to measure these. That's what I was going to do. That's definitely a 51 ohm resistor there. Okay, let's measure it. Let's give it a measurement here. trying to keep this on, view of the camera, but out of my way at the same time. Okay. 51, eh? Let's see. Going all over the place, isn't it? What's that all about? Could be a capacitor involved. I'm charging and discharging it. And every time I make a contact here, let's try again here. There. 32. Something in parallel with this. There's another one just right over here. Let's measure this other one. I'm sure it's green, brown, black. There we go. There we are. 54. That's what I would expect. 51 and plus a little bit for age. Let's go back to this one that's measuring low. And maybe I'm learning a lesson here I could have learned 30 years ago, and that is these resistors can go low if you overheat them, maybe without burning them out. Okay, why would we get 32 ohms instead of 51? Just one second here. So this one now has done the same thing. 1, 2, 3, 4, 5, 6. Yeah, it's done the same thing. So yeah, it's listed right there. So the AM radio one is section is shown here, and here's the 51. How do you not get 51? So the 51's here. I measured it here. It was fine. 54. This one's measuring low. Measuring low. Maybe I should go even further and say if you find a resistor and it measures low, it's been cooked. Maybe there's a rule there. So could you cook this and not fry this one? And I should check the value of this one too. The theory here is it's finding ground. How's it finding ground again? It would come down through here, through here. I don't know how it gets to ground here. What's this capacitor doing? It's going up. Is there a wire under here? I folded the page and eliminated some of the schematic here. Is it of some consequence? I don't know what this black line is. It looks like it's the edge of a page, and the photocopier did that. I don't know. A long time ago when I photocopied this. Photocopiers were still kind of new things. The high efficiency, easy to use photocopiers were still kind of new things. You had to pay 10 cents a copy to make this. I remember. You had to put the coins in a little box. We had a public photocopier where I was. Okay, enough of that. You gotta read this one. And again, I don't see how you get. So the idea is the B plus is coming up here. It's shooting through the shorted capacitor. It's coming down here. It's roughing up the 51 ohm and coming. Oh wait a minute, it could go up this way too, couldn't it? It could go up this way. But there's a resistance in these coils. And then I'm not sure what's going on over here. Oh, well, it's coming up, coming over, coming down, and then there's a capacitor to the. No, but see, this isn't grounded. This is kind of floating between tubes here. If I can put it that way, or is it grounded way around? I don't know. It's too much. No, you come up here, you hit a capacitor. I don't see how you can get a fault current to come down here. And maybe you can. I'm going to study the other schematic. Again, on the basis that just seeing it in a different format might help. Different layout is really what I should say. So starting again here. So we believe the fault is this resistor burned in two. Burned in two. And this one reading 90 instead of 500. I think I checked this coil, it's okay. Well, we should just be checking every capacitor in there to see if any of them are shorted. Maybe come back that way. Because trying to think this thing through is not working well. So we short this one. We'll pull a current through here. Burn this resistor. Now this resistor is open. But we still have a connection here. Where's this going? Down to another capacitor. So we shouldn't have anything. Unless now you want to talk another short. So let's forget this one. This one's good. This guy shorts. This guy shorts out. Is there a current path? Here it goes through the 51, through the coil, through the one. Look at this. I can see it quite clearly on this schematic. We got to measure this one, R103. I can see how this could happen. And so this, but I checked this and it's not shorted. So again, we go back to this healing up after shorting story, and I don't like it. I don't like going in and doing stuff when there's question marks everywhere. I don't like that. You want to get rid of the question marks. Okay, let's read this resistance. R103. R103. Let's get this out of the way here. Let's make sure we're looking at the right thing. Oops, wrong way. What was I looking at the right? Maybe I wasn't looking at the right set. So let's just check that too. So now I'm in the. This is how the radio was set when the event took place. I was not there for the event, by the way. I left the radio alone for quite a while. When I returned, it was. So is this the one that I checked? Maybe I checked the wrong one. I could easily do something like that. Okay, stay there. You can go over here. Shouldn't really be putting stuff on these plates here. Okay. Now, we're looking down at the right section. I'm going to rotate it. Okay, so there's the one resistor right there. This is the one it's a 51 that I've tested at, not 51. So I did this one. Okay, that's fine. That's fine. Now the other resistor is on the other side of this. I'll just go this way. There he is. How am I going to test that? I think I can. As soon as I put my hand in there, it kind of goes dark. I go down here. What was the size of this resistor? What was the size of the resistor? The size was, just check, it was 510, wasn't it? It's 510, 510. Like that. Okay, everybody watch. It might just be a momentary reading here. what? I don't think I can make contact. Oh, maybe. What was that? Okay, so there's no question I'm making contact at one end. Oh, it slipped off. Go back on it. Yeah, it's going to come up to 510. Or it's hanging around 510. It's jumping around. Why is it jumping around? So I don't think that resistor is shot. Let's take a closer look at it. I don't know if maybe I'm not going to get an answer to what happened here exactly, which I really don't like it at all. Okay, I'm going to attempt to take a close look at that. There he is. See the third band on it. This is a 510. How can that third band be orange? I'm looking again. That's a 510. There's no other resistors in this area. It's just the 51 and the 510. But this thing has an orange band. Yet it reads, what did it read? It read 450 or something. So is that evidence of it overheating? And the band that should be 510. That should be like green, brown, brown. 510, yeah, green, brown, brown. But it doesn't look like it, does it? But it doesn't measure bad. Oh my gosh, he's here again. Oh man. Can you not entertain yourself, little cat? Why is it always it's up to me to provide the entertainment for the cat? Once again, there he is. What is it? You want, look, your ball's right here. Here, look at this. Come look at this. There it comes. Mostly, yeah, he wants to play with me, not the ball. So, okay, I am going to stop here again. Not really getting anywhere at all. Okay, here's a new theory, but I'm not suggesting this is even a good theory. But so let's assume the resistance of this coil is very low and it's not playing a role, the resistance of it. Then the plate is seeing a resistance here of 500 ohms plus 1,000 ohms, 1,500 ohms. Here's the theory. What if the 500 fell to 100, as it seems to have done? Now instead of having 1,500 ohms here, you've got 1,100 ohms. What would that do? 1,100 ohms. I'm guessing it would increase the current flow in the plate circuit. So the question would be, would it increase the current flow, assuming this thing is dropping to 100 ohms on its own for some reason, and that would cause a sufficient current to I mean, this guy's already dropped, hasn't he? So something's gone wrong with him already to get this to happen. The heavy current burned this guy out. I squared R. So you have the same current flowing through these two things. And this R is, well, you know what? This R would be 10 times this one. So you get 10 times the heat developing here. So that'd be the scenario then. Capacitors are all fine. This guy's dropped in resistance. The result is this one burns out. And that's all that's happened. If I replace this and replace this, we're back in business. Obviously, I'm going to have to replace this and this. What if I replace these two resistors and then repeat the I was going to say then repeat the resistance measurements on the pins. But to do that, you have to put the entire piece back in the radio, wire it all up completely, and then find out I got to take it out again. So I don't want to do that. That's a good way to wear it to wreck this radio, putting that part in and out, in and out, in and out. Well, that's my theory at the moment. I don't have another theory. Maybe I can look into this a little bit further here, this possibility. Okay, there's another decision pending here with this, and that is, what do I do with all these capacitors in here? A few of these I took out, not from here, but from the rest of the radio, and tested them, and they tested perfect. They're perfectly fine. Yet I've had 3 of them, 2 of them fail actually. I thought the third one was in here, but I hadn't found a third faulted capacitor yet. So I've been told that these are highly reliable capacitors. They're special. My other Hammarlund radio, exactly like this one, was loaded with just ordinary paper wax capacitors, which I changed entirely. So a lot of work. It's like 50 or 60 of these, all told, in the radio. Many of them very hard to get at. And you know, in the course of doing that work, you can only imagine that the radio is never going to be like it was when it was new, even though you filled it with new capacitors. There's other components, resistors and that have drifted, and I'm not about to change everything in here and renew it. That's not where I'm going at all. I'd much rather just operate this with these capacitors in it. Now, there could be a risk to that, of course. When capacitors fail, they typically take something out with them. Not always, but quite commonly they do. If it's a resistor, it's not the end of the world, because you can find it, replace it, you know, a few pennies, who cares? Just some work involved. But if it's a coil, and a coil is what burns, then the situation is completely different. And I really can't tolerate, or I should not risk such a thing. So what I'm going to do, I'm going to end the video here, and I'm going to spend a little bit of time going through the schematic and studying each capacitor and trying to figure out if it's a risky capacitor to leave in or not. So maybe I'd end up replacing some percentage of the capacitors that I've determined are too risky to leave in. For instance, there's one, it's underneath down here, that I've replaced already, because if it failed and the fuse failed and the fuse didn't blow, some very important parts would be put at risk that you really can't even replace. So I think that I'm going to do this capacitor study, and that's going to help me make a decision about what to do. And that's it for now. So didn't really do anything today except a bunch of talk. But you know, talk. I've got a lot of that. Thanks a lot for watching, and we'll see what I'm doing here tomorrow. I have no idea. See ya.